How to obtain sound envelope using Python. Hello, I'm new with Python and also with sound signal analysis. I am trying to get the envelope of a bird song, zebra finch. It has a very rapid signal fluctuations and I tried with different approach. For instance, I tried to plot the signal and get the envelope with the following code based on other examples that I found. I added comments on the code to understand it. Here I tried two things. The first is use the resample function from scipy to get the envelope, but I have some problem with the signal amplitude that I don't understand yet. I uploaded the image obtained with the Fourier technique, but system does not allow me. The second is to use the Hilbert transform to get the envelope. Now I uploaded the image with the Hilbert transform again, the system does not allow me. It is possible to run my code and obtain the two images. But I'll put them with this link, this URL. Now the envelope fails again. I tried filtering the signal as I saw in some examples, but my signal is attenuated and I am not able to obtain the envelope. Could anybody help me with my code or with a better idea to get the envelope? It is possible to use as example any bird song. I can give you mine, but I need to see what happened with complex sounds, not simple signals, because it is very different. With simple sounds both techniques are okay. I also tried to add up the code that I found in this URL. But I am not able to get the proper parameters for my signal, and I don't understand the modulation part. I have already asked to the code developers, until waiting the answer.
Since with a bird song the modulation frequency probably will be much lower than the carrier frequency even with a rapidly varying amplitude, an approximation to the envelope could be obtained by taking the absolute value of your signal and then applying a moving average filter with say 20 milliseconds length. Still, wouldn't you be interested in frequency variations as well, to adequately characterize the song? In that case, taking the Fourier transform over a moving window would give you far more information, namely the approximate frequency content as a function of time. Which is what we humans hear and helps us discriminate between bird species. If you don't want the attenuation, you should neither apply a Butterworth filter nor take the moving average, but apply peak detection instead. Moving average. Each output sample is the average of the absolute value of, for example, 50 preceding input samples. The output will be attenuated. Peak detection. Each output sample is the maximum of the absolute value of, for example, 50 preceding input samples. The output will not be attenuated. You can low-pass filter afterward to get rid of the remaining staircase ripple. You wonder why, for example, a Butterworth filter will attenuate your signal. It hardly does if your cutoff frequency is high enough, but it just seems to be strongly attenuated. Your input signal is not the sum of the carrier, whistle, and the modulation envelope, but the product. Filtering will limit the frequency content. What remains are frequency components, terms, rather than factors. You see an attenuated modulation envelope, because that frequency component is indeed present in your signal much weaker than the original envelope, since it was not added to your carrier but multiplied with it. Since the carrier sinusoid that your envelope is multiplied with is not always at its maximum value, the envelope will be attenuated by the modulation process, not by your filtering analysis. In short, if you directly want the multiplicative envelope rather than the additive frequency component due to modulation, multiplication, with the envelope, take the peak detection approach. Peak detection algorithm in Pythonish pseudocode, just to get the idea.
The envelope of a signal can be computed using the absolute value of the corresponding analytic signal. Scipy implements the function scipy.signal.hilbert to compute the analytic signal. From its documentation, we create a chirp of which the frequency increases from 20 Hz to 100 Hz and apply an amplitude modulation. The amplitude envelope is given by magnitude of the analytic signal. Looks like. It can also be used to compute the instantaneous frequency. See documentation.
Signalprocessing